Welcome to ERC Tipsnology. This is part 3 of our programming timers tutorial about programming 8051 microcontroller using timer delays. So in this example 9-4, in the following program, we will create a square wave of 50% duty cycle. This means the portions for the high and the low signal is equal. So this will be done on P1.5 bit, and timer 0 will be used to generate the timer delay. But the question does not mention about the mode that we will be using. So let's just say we will be using mode 1, which is 16-bit mode. So it will be timer 0 mode 1. Now the program here is written in assembly, and you will see here this is just a part of the complete program. You will see here we have moved tmod hashtag 01. This means this is timer 0 mode 1, as given by the number 1 on the right, and the number 0 on the left is actually timer 1 mode 0. But of course we can use either timer 1 mode 0 or timer 0 mode 1, but because the we will take into consideration the one with the number 1. This means we are using timer 0 mode 1, which is 16-bit mode. And then we have here the here label, which is used to return to this part from here, whenever we have sjmp, like in the last instruction here in our assembly program, SJMP here, it will go back to here. And this will be repeated continuously. And within that, there's also another call for a delay function here. Unfortunately, the delay function here is not shown, but it will be something like a delay that will cause the timer delay, of course. Now, let's say this is the command move TL0 hashtag 0F2H. So this will be like we are moving the value F2H to TL0. So F means 1111 and 2 means 0010 in binary. So we are moving this number to TL0. Now, if this is C language, this is as simple as TMOD equals 0x01 semicolon, TL0 equals 0x F2 semicolon. And to move FF hexadecimal number to TH0 in C language, this is TH0 equals FF equals 0x FF semicolon. But here, this is assembly. So this is the command for moving the values, initial values F2 to TL0 and FF to TH0. Of course, in the question, it was not mentioned how long this delay would be, and we will just take into consideration that this is any value of delay, and then it will just negate or take the opposite value of P1.5 between 0 and 1, 0 and 1, and that will happen every time you repeat this loop, and this will be calling a delay function over here. Now, again, to calculate the values to be loaded into TH and TL registers, we can summarize it like we have to divide the time delay by 1.085 microseconds, and then the answer will be subtracted from 65536. But in other books and examples, we also subtract 1 from the 65536, which actually we get by getting the power of 2 to the n or 2 to the 16. You are using 16 for mode 1, and you will be using 13 for mode 0. So because the example here is 65536, I mean it it is representing the mode 1, because mode 1 would be 2 to the n, 2 to the 16, and that will be 65536. So minus the answer of delay divided by 1.085, microsecond. By the way, we got 1.085 by dividing 12 over 11.592 megahertz. Now, after that, we changed our decimal number answer here into hexa. And these hexa numbers will be four numbers like represented by YYXX. So the YY will be the TH and the XX would be the TL. So if we have, for example, 4BFD, 4B hexa will be for the TH, and the FD will be for the TL. So if this is 4B FD, 4B is for the high byte and FD will be for the low byte. You will see that more in our program. So in example 9-10, we have a crystal frequency of 11.0592. The question is, what value do we need to load the timer's register if we want to have a time delay of 5 milliseconds? So we have to show the program for timer 0 to create a pulse width of 5 milliseconds seconds on P2.3. So this example, if you're confused, it's simply as simple as we will make like an LED to blink between on and off every 5 milliseconds. And uh, to do that, if we are using LED, of course. Now, to do that, we can first calculate the time delay that we would use for 5 milliseconds. And again, going back to the formula given in this reference, 65,536 minus the delay divided by 1.085 microseconds. So that will be 5 milliseconds divided by 1.085 microseconds. We cannot divide millisecond by microsecond. So we have to change this to second, maybe by 5 multiplied by 10 to the power of minus 3, and 1.085 microsecond will be 1.085 multiplied by 10 to the power of minus 6. And there you go, you will get 4608. Of course, this is not the actual answer. I believe it will have a fractional part like 4608 point something. But we can drop that something or decimal part or fractional part because we just need to get the whole number. So in this case, the 4608 will be subtracted now from uh, 65,536. Again, we got 65,536 assuming that we are doing mode 1. That would be 2 to the power of n or 2 to the power of 16, and that's equal to 65,536. Again, why we use 16? Mode 1 is 16 bits. So in the assembly program here, the first part will make P2.3 equal to 0. The second part will move 00000001 to T mode in binary, and in hexa it's like 01 hexa will go to T mode. In C language we can simply write T mode equals 0x01 semicolon. So that means we want to use timer 0 mode 1, timer 1 mode 0, as we do in as we practice in part 1 of this tutorial series. So again, it's not true that we can only use timer 0 here, mode 1, because we can also use timer 1, mode 0. Now again, mode 1 will be 16-bit mode. Then we move 0 to our TL0. So the low byte TL0 will contain 0000, and the high byte will contain EE hexa, which is actually 14 in binary. That would be 1 1 1 0. So the EE here will be 1110 1110 if we represent it in binary. But just to simply make it hexa, EE will go to TH0 and the 0 will go to TL0. Then what we do is P2.3 will be equal to 1 And then we will start running the timer by set btr0. So the timer will start, and then we will jump to uh, we have here jnbtf0 comma again, which means that we will have a loop that will not do anything whenever the TF0 is equal to 0, or it's still 0. But when the timer flag 0 becomes 1, then it will stop looping between again and this. So it will not go to clear TR0 or clear TF0 unless the timer flag 0 is equal to 1, and that will only happen when the timer is done with its timing job. Now let's suppose that we are done using the timer, or counting up from 0 to the number which represents the 5 millisecond, which is EE00. So if we are done counting 5 milliseconds or timing 5 milliseconds, then automatically the timer flag will become 1, and the clear TR0 and the clear TF0 will be working. And it will stop the timer and it will clear the timer flag. As you can see, using assembly language is not that easy, but if you really understand assembly, this is what it would mean. Of course, we will be using C language also to see an easier way to do this. Now, moving on to the next part, we will be now doing the actual programming using C, and I will just be encoding the code for you. But I hope you like this video. Please like it, put some comments if you want, and share. Subscribe to my YouTube channel, How to Write an 8051 Program Using Timer Delays. Subscribe to ERC Tipsnology. So now let's say that we will be writing a program for uh, like blinking an LED. So let's have some sort of a review. How do we write a program that will blink one LED in using an 8051 microcontroller? So it would be better maybe to write the question here, like an LED is connected at port P1.0, and what we will do is we will make this LED to blink. So we'll make an 8051 C program that will toggle or blink this LED every uh, 1 second. So we will use timer 1 in mode 1. Now the first thing that you have to do, of course, is to do the calculation of the initial values of TH, TL, and TH. So this TH, TL, and TH are the registers for the timers that we will use. So we need to know the value of TL1, because we are using timer 1. That would be what will be the value of TL1, and we want to know, of course, the TH1 also. Now the formula that we can use to calculate the initial values, there are different interpretations for the calculation. So just to copy the steps that we are doing before, what we do is we will have 2 to the power of n, or we raise it to the power of n, and then we subtract the delay, but this delay will be further be divided by 12, divided by the crystal frequency. So this is the formula. Now, in other books, we also have other formula like 2 to the power of n minus 1 followed by delay divided by 12 divided by the crystal frequency. But following this tutorial series, we did not really subtract 1 from 2 to the power of n. Now, mode 1 is 16 bits. So what will we do is we will be using 2 to the power of 16 in our calculation. So uh, to calculate for the initial values, it would be 2 to the power of n, 2 to the power of 16 minus the delay, which is 1 second, divided by the 12 over 11.0592 megahertz. And of course, if you calculate for this, we will have an answer of 65,536, and we will subtract uh, 1 second. But when you calculate 12 divided by 11.0592, the answer will be 1.085 microsecond. And if you want to calculate this, continue to calculate 65,536. We will get equal, let's make it the same unit. So it will be 1 million microsecond divided by 1.085 microsecond. And you will find here that the answer will be negative if you subtract for this. So let's try to get a calculator here so that you can see the answer. So if we have 1 million and you divide it by 1.085, we will get an answer of 921,658.98 or 986. Now, if I copy this answer and I subtract it from 65,536, if we subtract it from there, 65,536 minus the 921,921,000, we will get a negative answer of 856,122.98. So that's the answer we will get. And as I have said before, negative value. So we need to use another delay value. Example, we can make use of 10,000 microseconds. So so that when I calculate for this, instead of subtracting a huge number from 65,536, we will just be getting a value that will not make the answer to become negative. So, like in this case, the answer, if you have something like 65,536 minus, I mean, 65,536 minus the value of 10,000 divided by 1.085, the answer will just be 56,319.41. So this is what we get from our calculation. Now we can drop the 0.41 here. So we will just get 56,319. And then this 56,319, we will change it to hexa number. So what will it be? If we change it to hexa number, so we will have 56319. Change it to hexa, it will be dbff. So that's what will happen. So it will be dbff. And because of that, now we have our TL will be equal to FF, and our TH will be equal to DB. So to get the initial value. Now, because we want timer 1, so TL1 equal to 0x FF, and TH1 will be equal to 0x DB. Oh, so there you go. This will be our initial values for our timer, and what we will do. But remember, this is only for 10,000 microsecond. So we need to have a loop that will repeat this 100 times, so that what will happen is 10,000 microseconds. If you multiply it by 100 times, that will become 1,000,000. That will be equal to 1 million uh, microseconds, and this is actually one second. So there you go. That's how to calculate first for the initial values. Of course, when you do this, you have to take into consideration what is the mode you are using. Now, if it is not given in the question, you can simply use mode 1 to make it more easy for you to do the problem. Now, let's write the program now to blink the LED. So again, we'll blink the LED on P1.0 every 1 second. So to do that, we use the hashtag unsigned, hashtag include uh, reg51.h, and then we have unsigned uh, int x, and then we have sbit p10 equals p1 caret 0, and then we have the main void. Let's have a revision or review first of using any delay. Okay, using any delay. So this will be our program. This is using any delay. And of course, we need to put the bracket here, the open curly bracket, followed by the what will you do with your port? P10, will it be input or output? So we use 0 to make it an output port. And then we have while one, and this will repeatedly do the loop continuously without stopping. And what we will do is we will simply make P10 equals to tilde P10, and then we will put the any delay. So for x equals 0, x less than 10,000. So this is how we do it without any timer delays. So the first line is required. The second line here on 30 unsigned int x, we use it for our delay using the for loop, and s bit p10 equals p1 caret 0 just to declare the port 1.0, and the void main void up to 38 is what we usually do. And then we have p10 equals 0 just to make port 1.0 as an output port. And if you want to make it an input port, we put 1. But now it's an output port because it's an LED. And while 1 to repeatedly do whatever is between 35 and 36 on line 35, this will toggle or blink the LED on port 1.0. And 36, this is the delay or using any delay. So we use 10,000, 0 to less than 10,000, it will count 10,000 times. Now, let's say this is not using any delay. We are using timer 1, mode 1. Isn't it? That's what I wrote here, timer 1, mode 1. So to do this, we will no longer use the delay here. Instead, we will just write the name of the timer delay. For example, we can call our timer 1 delay T1 M1 delay. Although it's too long, at least it's clear what it is. So timer 1 delay, but because you used a user-defined function, you have to put it here by declaring that void T1 M1 delay. Then you put void again here and open curly bracket, and then you put here what your timer will do. For example, T, the first part, of course, T mod equals 0x, and then you put what timer and mode will you use. So we will be using timer 1, mode 1. So as we have used, as I have explained in the part 1 video or part 1 and part 2, this will be timer 1, so 1, timer 1 mode 1, and the other one timer 0, keep it mode 0. So that's how to do it. And then we need to describe or tell what will be the TL, the TL0, what will its value be? 0x, as we have calculated here, it would be FF. So we have here FF. And then the TH, we have to tell how much is the TH. So it will be 0x dB. Therefore, you cannot run the program without identifying what is the value of your TL and TH. And then we will run the timer. So we put TR0 equals 1. And then we will continuously check if the timer flag 0 is still 0, then we do nothing. This means that the timer is not yet done in its timing job. So next, if it is equal to 1, it becomes equal to 1 by itself. Then the timer will be stopped. So we put TR0 equals to 0. And after that, we put TF0 equals to 0. Just that's to reset the timer flag to 0. By the way, the timer flag 0 equals 0 again is checking whether the timer flag is done in counting up or with its timing job. So if it is not done, it will not do anything, do nothing here. And it cannot go to 38 and 39. But the moment it is done, it will become false and it will do TR0 and TF0 to become 0. That's it. And then we close the bracket. And this is actually now your timer program or timer programming using 8051 microcontroller. And this is using the timer 1 mode 1. So this is the complete program for that from number 29 up to here. So I have showed you. Now, other books, what they do or other references, they remove the function here and put it down after the main. But because of that, you have to define or to declare your timer delay function at the top before the main. So that's it for this session, and we will continue on the next part.